Okay, hello everyone. This week, week number 10, uh, we're gonna begin with some brief understanding how the carriers are flowing for a given volume of silicon material. So to describe mathematically how the carriers within a silicon material are moving around, maybe under a condition of electric field or under any gradient doping concentration stuff. So we're gonna write down the mathematical equation to describe how carriers are moving around. Okay, so the basic equation to express how the carriers within a silicon material is moving is continuity equation. So continuity equation will be studied first. Afterwards, with some simplifying assumptions, um, well, to make the complicated continuity equation simple and simple, we're going to use a few, maybe seven different assumptions to simplify the continuity equation. Then we're going to obtain the minority carrier diffusion equation, which will be used to analyze the PN junction diode. Okay, so minority carrier diffusion equation is the key knob uh, in explaining how the current is flowing in a PN junction diode. Afterwards, uh, we're gonna figure out a new physical concept named as minority carrier diffusion lengths, which will be included in the minority carrier diffusion equation. Okay, and then we're gonna wrap up this lecture note number 10 with a brief introduction on quasi-Fermi levels. So the corresponding sections in the textbook is 3.4 and 5. So please read all the sentences in those sections. Okay, so let's take a look at this slide. Uh, Derivation of a continuity equation. So I'm briefly telling you how to derive the continuity equation. So let's consider a carrier flux in and out of an infinitesimal volume as drawn here. Very small volume for a given small volume. Say the volume is A times dx. So A indicates cross-sectional area denoted as A, and the side length of this infinitesimal volume or cubic is dx, very small x, right? Dx. So A times dx indicates the volume of this infinitesimal uh, cubic. Okay, and now suppose that a carrier, maybe hole, is moving into this infinitesimal volume, and afterwards is going out of this infinitesimal volume. Okay, then how those holes are carried out from left to the right hand side. So here on the left hand side, you can see that two major terms. So here A times dx indicates, volume, right? And the second term indicates, n. What is n? Yeah, the number of electrons per volume, right, for cubic centimeter. So if we multiply volume times this, then the unit for volume will be cancelled out. So in the end, we're gonna get that number of electrons. Okay, but I have missed the one unit, right? As you just noticed, the time here, t. Okay, so here times second. So every second per given cubic square centimeter, per cubic centimeter, how many electrons are varying? Okay, because I am using the first order of derivative. Okay, so dn dt indicates how many electrons per unit volume per second are varying. Okay, but here the volume that we are interested in is very small volume, infinitesimal volume, with the A times dx volume. Okay, so if I do multiply A dx, this guy, times dn dt, indicates every single second how many carriers. In this case I use the n, so electron is moving. Okay, so here just to sync with this equation, I'm going to use the electron as a carrier. Okay, so on the left hand side, ADX times dn dt indicates how many electrons are getting in and out every single second. Okay, let's take a look at the right hand side now. Since electron is moving, which means current is generated. As you know, the opposite direction of electrons movement is defined as the current flow. Okay, so maybe in this case, if electron is getting toward the infinitesimal volume, then the current is flowing uh, from right to left hand side by electron. But it doesn't matter. It doesn't matter. In this case, suppose that the current is flowing from left to right, and at x. So here, x-axis indicates the physical distance, and this left-hand side here indicates x is x. And here, the surface where the electron is moving away is x is equal x plus dx. Okay, because we have defined that the side length of this infinitesimal volume is dx, very small variation of x. So the left side, or how to say, just the left edge is x, right edge is x plus dx. Okay, then the current value at x is defined as Jn of x, and the current value at the right edge is Jn of x plus dx. Okay, uh, the thing that we need to figure out and we need to know is how many carriers are varied every single second. Okay, so what kind of physical quantity should be included to match with the unit on the left hand side? So let's think about this. Electron is moving, or hole is moving, any type of charged carrier is now moving, and they are generating the current. But definitely this J indicates current density. So for given area, how much current is flowing. So J is defined as current divided by area, amp per square centimeter. Okay, so the current density is now given as J sub n of x. But at the right edge, the current density should be modified because some magics, something would be occurred within this infinitesimal volume. We have no idea what kind of things and what kind of events would be happened within this small volume. So we have no idea, but we have measured the current density at x and at x plus dx. So it was determined that the current density at x is Jn of x, and current density at x plus dx is Jn of x plus dx. Now, on the right hand side here, we would like to write down some equation to get this unit, number of electrons or number of holes or number of carriers divided by time. What kind of things should we write down? Yes, the answer can be found here, but you can do that by yourself. So we know the current density. So if I multiply the cross-sectional area, then it's going to become current. What is the unit of current? Yeah, amp per, no, sorry about amp, and that is identical to the coulomb per second. Okay, so now I would like to know how many number of carriers per second, but this guy indicates coulomb per second. So what else do we need to have a matched unit on left and right hand side? Yeah, second is here and there, so we are okay. And now number of carriers, but here the charge. Then in this scale, we need a number of carriers divided by coulomb. What is this? Number divided by coulomb. You know this, number per coulomb. No, sorry about this. Coulomb per number. Say you have 10 coulomb, but you have a 5 electron. Then each electron would have a 2 coulomb, right? So what is the physical quantity to do this role? Yes, unit charge, small q, right? Small q means uh, the total charge of a single charged particle. Okay, so coulomb per number is q, right? But here the thing that I need to have is a number over coulomb. So and here in 1 over q is necessary. Okay, so J times A times 1 over Q. So this number indicates the number of carriers divided by second. Okay, we're almost done. Now let's erase my note and take a look at here again. So now the carrier is moving into and out of the volume. How much, carriers are killed or generated? I mean, how many carriers are recombined within this volume and how many carriers are newly generated? We have no idea because I didn't give you any information on the events happened within this infinitesimal volume. So the only thing that we can monitor is the current density in and out. Then we may do this current density variation. How much current density has been changed across x direction? Okay, so Jn x plus dx times a means the current itself indicates the current value at x plus dx, right? And minus Jn x times a. What is this value? Yes, the current value at x. So I say here is initial, and this position is matched corresponding to the final. So final and initial stage. Final stage, initial stage. Final spot, initial spot. In Korean, 나중 minus 처음. Okay, so in calculus, in 미적분학 in Korean, in calculus you may have learned how to estimate how much variation is happened for given two different spots. Yes, 나중 final destination is x plus dx, and the initial place is x. Okay, and this value indicates the final the current value at final spot, and this current value indicates the initial current value. Okay, so final current value minus initial current value. So we have calculated the difference between two two different current values, final value versus initial value. And how long was the distance between two spots, final spot and initial spot? Yes, dx in the end, right? X plus dx minus x is equal to dx. Okay, but this total unit is not well matched to the unit for the left hand side. Therefore, we should do multiplication of 1 over q, where q is unit charge. Okay, so these all equations has been well write down here. Of course, this minus should get into the parentheses, then into this bracket, then you're gonna get my equation as I have just write down. Okay, here. All right. So this very first term indicates how much current has been changed. However, because we have used the 1 over q, the very first right term indicates how many carriers, number of carriers per second. So every single second, how many carriers are varied, modified, while those carriers are traveling across the infinitesimal volume. So previously I mentioned that we have no idea what happened within this volume, but we can monitor the voltage, no, the current density difference. Okay, so from these two different measured current volume, current density, we can estimate the number of carriers per second. Okay, all right. Well, while building up the continuity equation, this first term would be good enough to be matched to the terms on the left hand side, but unfortunately that's not always true, because some events would be happened within this volume. So herein, while building up the continuity equation, we have assumed that two things: recombination and generation. Simply speaking, the two electron has been injected into this volume, and the 4 electron is now emitted out. What happened within this volume? Well, 2 more electrons are created. Then 2 plus 2, total 4 electrons are emitted out. That's true. But I would say, you said 2 more, but no. 4 more electrons would be newly created, but 2 electrons are annihilated or recombined with holes. So 2 electrons has gone. But in terms of the net number of electrons created within the volume is still 2. Then 2 plus 2 is equal to 4. That's true. The very first equation, the first term only indicates that this guy, 2e and 4e, how many carriers are varied. But this first term cannot explain some more hidden events happened within this infinitesimal volume. So herein, the author has provided one case, recombination. A few electron has been injected within this within this volume, but part of it has been recombined with holes. So rest of the electron has been emitted out. So herein, how many electrons are recombined with holes? So here you can see the minus sign. That means the number of electrons per time, every single second, is decreasing. So this minus sign indicates a recombination. Okay, and next thing is how many carriers are killed by by holes. Uh, the information that we know is this: delta n and tau n and a times dx. What is this? A times dx means the total volume of this small cubic. And what is this delta n? Yes, excess electron concentration. What is this? Tau sub n. Yes, minority carrier lifetime. So in this specific example, the author has assumed that this small volume is a p-type silicon material, so hole is majority carrier. And since there are too many holes, once a small number of electrons is injected or absorbed into this volume, then the electrons would be recombined with holes. Okay, then let me see. Okay, so the thing that we need to know is this number of carriers per second. Maybe the carrier in this specification, specific case is an electron. So we have how many electrons has been excessively, additionally injected into this volume. Well, this volume itself has a certain amount of electron. So I use the n sub naught. That means at thermal equilibrium, before this current is flowing, this sample has its own electrons, which is denoted as n sub naught. But because of this current flow, more electron has been injected. So the variation of electron concentration can be denoted as delta n. That is, defined as excess electron concentration. So this number, delta n, would become zero if time is uh, going forever, because the injected electrons would be recombined with the holes at time of infinity. If time is infinite, then all the injected electrons would be recombined with the holes. So delta n would become zero. In other words, n time infinity should be equal to n naught, because everything would asymptotically move toward equilibrium state. Okay, but herein, this amount of newly injected electrons are available in this infinitesimal volume. And the thing that we would like to know is how many electrons are still alive every single second. So we need to figure out how long the injected electrons, how long once electron is injected in this volume, then how long it can survive. The answer can be found here, lifetime. What was the definition of the lifetime of minority carrier? Yes, in the sea of majority carriers, how long the minority carriers can be survived without or right before being recombined with the host or majority carrier. So the thing that we need to is number of carriers per second, right? So suppose that this lifetime is 1 microsecond. That means every 1 microsecond, one electron would be killed by holes. But the information that we need to know is every 1 second, not microsecond, a single second. So tau sub n delta n. So this unity, this physical amount quantity would give us the idea, the number of carriers per second. But herein, this delta n indicates number of electrons per cubic centimeter divided by time. So we should take care of this volume. So to cancel out this volume, we should do multiplying ADX, the volume. Okay, so now take a look at here. Delta n over tau n times ADX. That is well matched. The unit of this guy is well matched to the number of carriers by divided by second. And here again, minus sign indicates a recombination. The total number of injected electrons would be decreasing and decreasing because of the recombination. And what about the generation? Well, in this case, the generation would be always occurred together with the recombination. But herein, I would like to say that the light has been exposed. Then this light would generate the electrons and holes together. Okay, so GL means number of carriers every second. Okay, so plus GL. So you will see this new term on the next slide, plus GL. So G indicates generation, L indicates light. So if any external force, such as light, would be applied onto this infinitesimal volume, the light would contribute to create electrons and holes. So this number would affect uh, round n round t times ADX. In other words, number of carriers divided by second. So again, here the basic idea for this continuity equation means if something is input, some others would be output. But some magic, some other events would be happened in this volume. Then we should take into account those new events. So 10 electron has been input, 10 electrons output, then no internal variation happened. That's very simple. But say 9 electron has been input, 12 electron has been output. Then what happened within this volume? Yes, some internal variation would be happened. So in this silicon material, what kind of detailed, specific internal events would be happened? With your knowledge, with the things that you have learned is recombination and generation, right? So herein, this term, second term on the right hand side indicates a recombination. And if the light is included in this case, then generation by light would also contribute to the number of carriers divided by second. Okay, so we all set to understand and to mathematically write down the continuity equation. Left hand side indicates how many carriers are varied every single second. That is the final, final goal that we would like to know. On the right hand side, suppose that the current is flown into the infinitesimal volume and the other amount of current density has been output, then some other internal events would be happened within the infinitesimal volume, such as recombination and generation. Then we should put everything together on the right hand side and then we can balance out the unit of left hand side and right hand side. That's it. That's a basic process and steps to build up and to derive the continuity equation. Okay, so now let's move on to the next slide. In the previous slide, we should make a simplification of this continuity equation. So take a look at these two guys. Okay, and what is the uh, definition for current density variation? I mean, the current density, how much current density has been changed with respect to x? How to write down it? Yes, very simple. X plus dx minus x and current density minus g and x. Yes, that's it. And x are cancelled out. And if I move dx here, dx here, and now I'm going to move this term on the left hand side toward the left hand side. Then jnx plus dx is equal to jnx plus on to jnx on the x dx. Okay, so this equation has been be could be found can be found in the very first line. Okay, then now let's name it as equation number one, and remember the equation number one and bring it into here. Okay, so replace jn of x plus dx with the equation number one here, plug in it, then rearrange all the other terms, and you're gonna end up with a round n over round t is equal to this. Again, the GL has not been included yet, but in the final stage, the author of the textbook has included the generation rate by light. Okay, so this generation rate by light indicates the number of carriers over second. Okay, so now round n, round t, how how much electron concentration has been varied over time can be understood with these three different terms. Okay, so how much current density has been modified along the x direction, and how many excess electron carriers are recombined with the majority carriers for given lifetime, and how many new electron hole pairs, how many new holes, how many new electrons are created by light, then this term would be contributing to this round n, round t. Okay. On the last line, you can see the same, almost same equation other than, n and p. Okay. So instead of n, use p. Then you're gonna simply derive the continuity equation shown on the last line. Okay. Okay. So that is a very generic form of continuity equation. That continuity equation itself cannot be used in analyzing how the p-n junction diode is working. We're gonna put and we're gonna take advantage of using some simplification assumptions to make the continuity equation simple and simple. So let's do some more. Let's see here. From those previous two slides, we have derived the continuity equation. From now on, we're going to derive the minority carrier diffusion equation from the continuity equation. Okay, so minority carrier, so I guess for your information, we have a p-type material and n-type material. Those are two different silicon materials that are contacted physically together, and now the n side is grounded and p side is biased. So suppose that you are applying positive voltage onto the p side material. As you know, p side material, p-type material has a bunch of holes, and n side material has a bunch of electrons. Okay, if you are applying positive voltage onto the p-type silicon material, these holes would move toward n-type. Okay, once hole is injected and arrived at the n-type material, this hole becomes minority carriers, right? Then afterwards, once the hole is arrived or injected into the n-type material, then hole is still moving toward the edge of the n-type material because still positive bias has been applied. So we would like to write down the equation how this hole, this minority carrier hole, can be diffused or not yet diffused, can be moved. How those electron injected holes are moved toward the edge of the n-type silicon material. I would like write down the equation to mathematically express these holes movement in the n-type material. So I said hole movement in the n-type-material, which means hole as minority carrier in the n-type-material, right? So minority carriers are moved in the n-type-material. So now let's change the color, and now let's take very small infinitesimal area. Well, this p-type n-type is three-dimensional sample, right? So let's take out this infinitesimal volume. I guess I need to write down, okay. So p-type, n-type, right? So hole is now injected here, and I would like to write down the very small infinitesimal volume. Okay, so now hole is injected and output. So this specific case would have already explained in the continuity equation in this slide. Same, right? Hole is now moved toward the infinitesimal volume, and they are output. And some events would be happened within this area, well, recombination or generation. So same thing would be happened, well, same thing would be happened here, right? I guess my drawing has gone p-type, n-type, and the hole is now injected, and hole is now moving toward the left edge of this infinitesimal volume of an antimaterial, and they are going to be output from the infinitesimal volume. So within this infinitesimal volume, recombination generation would be happened. Okay. Now we can use the continuity equation how the whole concentration would be varied over time this term. Okay, you can write down the equation for this from slide here, right? Okay, you can write down it. However, this equation is still very complicated, and the reason why we are studying the continuity equation is to explain and to have some deep understanding how the holes in the antimaterial is moving. So, uh, especially for PN junction diode in the end. Okay, so once positive bias is applied onto the P side and hole is now injected into the N side, and now this hole is moving throughout this small volume. Then what kind of things are applied in this specific area? You're gonna learn that later, but in this you know the area away from the physical contact area of PN diode. Let me write down two-dimensionally PN. Okay, so this physical area, if hole is now arrived very away from the physical contact area, then this area, I say this area, it has very small electric field. So many students has had a chance to learn the p-n junction diode theory in undergraduate class. So you may hold that the positive voltage is applied here, and most of the voltage should be dropped across the depletion area. Okay, here. So here and there, say 1, 2, 3. So reason the area number 2 is corresponding to depletion region. So most of the voltage that I have applied has been dropped across the area number 2 or depletion region. In other words, the voltage difference or the voltage drop across the area number 1 and area 3 is negligible. In other words, the voltage difference is zero in this specific area. Well, we're gonna learn it later, but this area is named as quasi neutral region. Okay, so simply speaking, QNR. So quasi-neutral region, there is no voltage drop. In other words, no voltage drop means a no voltage difference. From where to where? Yes, from the edge of the depletion region to the edge of the antimaterial. So within this quasi-neutral region, there is no voltage difference. No voltage difference. Delta V is zero, which means it's still zero. That means the electric field. The definition of electric field is voltage difference for a given distance. Okay. Even the unit for electric field is volt per centimeter, right? So in this QNR region, there is no electric field. No electric field means no drift, right? What was the definition of drift? Yes, under a given electric field, the charged particles would be accelerated by the electrostatic force coming from the electric field. You know that force F is equal to minus Q times electric field E. But now E is zero, so force is zero. No force means no acceleration, right? So no drift can be happened. So in quasi-neutral region of p-n junction diode, okay, the area number 1 and 3, as I have drawn, in those are two QNR regions, no electric field, that means no drift, which means again, no drift current, okay? So now in the continuity equation here, let's take a look at the Jp of x, the current density by electron, by hole. Jp, total current density by hole. Yeah, Jp. As we have learned in chapter 3, 3.1 or 2, I cannot remember the exact subsection, but we have learned that total current density by hole and by electron. Jp is equal to Q times mobility of hole times mu p, and the hole concentration times electric field. And I guess this is typo, minus diffusion current density. That is Jp drift. That is Jp diffusion. But now this electric field in the quasi-neutral region or area number 3 in p-n junction diode, this E is almost zero, no electric field. Then Jp in the n-type silicon material can be denoted as Q times dP. Again, the minus symbol has been missed. Minus Q times dP times round P over round X. Okay, so this can be plugged into here. Okay, we're gonna use that later. All right, this is the very first simplifying assumption to be used in analyzing the p-n junction diode. Okay, so now minority carrier diffusion equation can be derived from the continuity equation and with the help of a few simplifying assumptions. One of which is the electric field is very small in the quasi-neutral region of p-n junction diode, so that in n-type material of p-n junction diode, the whole current density Jp herein can be denoted as minus q times dp times round p over round x. That's it, because the electric field is almost zero in the quasi-neutral region. This would make our life much easier when uh, writing down the minority carrier diffusion equation using this continuity equation. Okay, so we're gonna use this term with replace that term with this. Okay. Okay. The second simplification is n naught p naught are independent of x. That means for given silicon material, whatever it is, whatever the silicon type is, p type, n type, along the x direction, the doping concentration is always uniform, so that the electron concentration and hole concentration at equilibrium is almost constant. Okay, so to implement or to obtain the constant electron hole concentration, we need to fabricate uniformly doped p-type and n-type silicon material. All right. The third simplification is loadable injection condition. Loadable injection conditions prevail, dominant. So this condition is very dominant. What kind of condition? Yes, loadable injection. Loadable injection means hole has been injected into the n-type material, but this number, these injected holes would not make change on the majority carrier concentration, in this case, the electron concentration. Okay, these injected holes cannot affect significantly the majority carrier concentration. Okay, however, the minority carrier concentration in this region, n-type region, it, this is anti-material, so the minority carrier is whole, right? So the whole concentration at thermal equilibrium, P sub naught. This P sub naught would be changed a lot to what? Yes, whole concentration. And this P would be dominated by these injected holes. Okay? Then low level injection condition prevail. Okay. All right. Now starting with the continuity equation for electrons, I have brought the continuity equation for electrons here. Going back two more slides, and you will see that this equation. So I'm going to copy and paste here. Okay, and now this guy. Okay, and this guy Jn of x. Yes. What is this? Yeah, go back to the previous slide here, and electric field is small, so you can just use this. Okay, so plug in here q round x here, round x. So Jn has been plugged in into this bracket, but again here that was n. So we have defined that excess electron concentration is defined as delta n is equal to n minus n naught. So n is equal to n naught plus delta n. So instead of n, I have used the n naught plus delta n. And there we go. Instead of n, I have used the n naught plus delta n. And the other terms, this guy, second and third terms are still there. Okay. And one more thing that I have done from second line to third line is this guy, n naught. N naught means electron concentration at thermal equilibrium. So over time, this number n naught cannot be varied at all. Therefore, if I take a first derivative of n naught with respect to time, this value would be 0, right? So only delta n has been alive. Same here. N naught can be removed because N naught cannot become alive over time. And here, the reason why I have removed N naught is independent of X. Why? The N naught is always equal to all X values. Go back to the simplification assumption here. Take a look at N naught are independent of X. So if I take a first derivative of N naught with respect to X is 0. Okay. So we can remove this term as well. Now let's rearrange all the terms. So here we can remove, then you're gonna get this. And here Q and Q are canceled out, and Tn is a diffusion constant, right? So constant can be placed here, and you're gonna take a derivative of delta n with respect to x 2 times right here and there. So you're gonna take a second order derivative of delta n, and these 2 terms are still there, still existing as they are. Okay. All right, we almost done. Almost done here. Take a look at this equation and take a look at this equation. Almost same, other than subscript P has been included. Otherwise, same. So what is the meaning of the subscription, P or N? So now let's take a look at the meaning of subscription. Herein, subscript N or P is used to explicitly denote N-type or P-type material. So if I write down P sub N, which means whole concentration P, right? Whole concentration in the N-type material. What about this? P sub P. P sub P indicates a whole concentration in the P-type material. Okay, so PP means a majority carrier concentration in P-type material. And Pn means minority carrier concentration in N-type material. Okay, what about the N sub P? Yeah, electron concentration in the P-type material. Okay, I guess this is type of P-type material. What about the Nn? Yes, electron concentration in the N-type material. In other words, majority carrier concentration in the N-type material. What about this? N sub P means minority carrier concentration in the P-type material. I guess N, P, yes. Okay. So those are 4 guys: PP, PN, NN, NP. So you should remember those are 4 different notation. But herein, the equation, this has been obtained from the continuity equation, and we have used the 3 simplifying assumptions, right? And one of which is the electric field is small. Why is that? Remember the PN junction diode again, and hole has been injected into this N-type material. So here no electric field because this quasi-neutral region has a no voltage drop across it. So hole in the N-type material, right? That means hole is now minority carrier, and this minority carrier is moving toward the right side, right edge of the N side. So that first order equation, I mean this first order equation, if I write down it, maybe this, right? Whole concentration in the N-type material. So this minority carrier diffusion equation would be only valid in the N-type material. Okay, and this minority carrier diffusion equation is only valid in the P-type material. When it comes to the electrons in the P-type material, this equation number 1 can be valid to describe, explicitly describe how the minority carrier in p-type material. In other words, how electrons in the p-type materials can be moved. But I have used the diffusion, the word diffusion. Instead of movement, I have used the diffusion. Why diffusion? Why diffusion? Yeah, go back to the PN diode again. And now the hole has been injected and it is going toward the edge of the inside material. But here, no electric field. Then what is the main mechanism for hole's movement? Drift is not available option because there is no electric field. So that diffusion is the only option to be left. Okay. But physically, many holes are now injected into the inside. And here, no injected holes. But here, many injected hole. So in terms of hole concentration, the hole doping concentration would be higher near to the PN junction side. Okay, so the hole was diffused toward the edge of the N side. So now, whenever we are talking about the hole is now moving in the N side of PN junction diode, yes, hole is now diffusing. Okay, so now let me summarize it. So for a given PN junction, the hole has been injected toward the N side because of the positive voltage applied onto the P side. And these holes would diffuse toward the edge of the N-side material. Question is how those minority carriers in this specification holes in N-type material can move. How moving? Yes, diffusion. Can you explain it mathematically? Yes, I can do that. That diffusion can be described by and can be governed by these second order derivative equation. In Korean, 2차 미분 방정식 for holes can give us a hint how the holes can be moved in the N-type material. Okay, so now you're gonna get some idea why diffusion equation. The name is diffusion equation instead of drift equation. Okay, and now you may understand why minority carrier instead of majority carrier, because we're talking about this area. Why minority carrier? Go back to the simplification assumption here. Electric field is small. In PN junction diode, okay, there is depletion reason. Here and there, no electric field. That okay. All right. I guess what time is it? We have spent almost 1 hour, so I guess it would be good time to have a short break time. So please review what we have learned. Yeah, from the first slide, we have come up with some idea how to describe the electrons and holes or carriers are moving into and out of an infinitesimal volume. So we have completed how to write down the continuity equation, and the unit for the left-hand side and right-hand side was a number of carriers per every second. Okay. Afterwards, we have used the three more simplifying assumptions. Electric field is small, no electric field, and N naught P naught independent of X. In other words, if I take a derivative of N naught with respect to X is 0, right? And the loadable injection condition prevails, so the majority carrier concentration cannot be affected a lot, but minority carrier concentration should be affected significantly. So with that in mind, we have finely tuned the minority carrier diffusion equation from line number 1 to line number 3. Afterwards, we are gonna put some more details such as a subscript N or P. Those subscript indicates N-type or P-type material, so Pn and P. Then we're going to have some more detailed and perfectly written minority carrier diffusion equation. Okay, so please remember these two equations in your brain and review. See you in the next movie clip.